Hello, everybody. Welcome on our last seminar in this semester before winter holidays. Today we had a guest from University of Gdańsk, Krzysztof Szczygielski. The title of his talk is Non-additivity of minimum output Rényi p-entropy of quantum channels. Krzysztof, please start.
Thank you very much. Thank you for the introduction, and of course, many thanks to Rényi for invitation. So today I would like to share with you some of our recent results concerning non-additivity of Rényi p-entropy, and this is a joint work with Michał Studziński, who was supposed to be here actually, but for some reason he is not. Okay, so I will start with some really basic notions. I'm pretty sure that you know all of this, but let me tell you anyway. So let's consider two Banach spaces of trace class operators acting on some Hilbert spaces H and K. Okay, so we have two Banach spaces, and we define the set of all density operators acting on the Hilbert space H. Okay, so that will be the set D of H. As the subset of positive semi-definite operators of trace 1. Okay, and the basic, of course, this is just a basic fundamental stuff. Let me define the most, let's say, basic object that we are interested in, namely the Rényi p-entropy. Okay, so let me select a p as a parameter p from positive axis apart from 1. Okay, and the Rényi p-entropy of some given density operator rho acting on H will be given by the following formula. Okay, the SP of rho is 1 over 1 minus p times the logarithm of trace of rho to the power of p. Of course, in general, this is, let's say, infinite dimensional setting. So this rho to the power of p must be defined in according to functional analysis, but because of some sophisticated properties of rho as a trace class operator and so on, we know that such trace is simply a summation, okay, over all eigenvalues raised to the power of p. When p is greater than 1, then from properties of rho as a state, we know that such sum always converges. However, in the case p less than 1, it doesn't have to be so. But we will be interested in finite dimensional setting. Okay, so again, we are assuming that both H and K are just finite dimensional complex Hilbert spaces. So the definition will be the following. Let me assume that I have a phi, which is a completely positive and trace-preserving map acting, between Banach spaces of trace class operators acting on finite dimensional spaces. Okay, so this is a quantum channel. Okay, we define the following object, namely the minimal output p-entropy, which I will denote by SP minimum of phi, which is actually the minimum of all of the entropy calculated with respect to given density operator rho. Okay, but because of convex structure involved here, we can further simplify this formula by minimizing just over all rank 1 projections onto one-dimensional rays. Okay, in Hilbert space spanned by vectors of unit norm. Okay, so this minimal output p-entropy is actually the object we are interested in. Okay, so what actually we know about this minimal output p-entropy, especially in correlation with so-called additivity breaking? What we know for sure is that the minimal output p-entropy is a subadditive function. Okay, so this means that if I have two quantum channels okay, namely two completely positive and trace-preserving maps, phi1 and phi2, between those spaces, then the minimal entropy of the tensor product is always less or equal to the sum of minimal entropies, okay, calculated for phi1 and phi2. This property actually translates to the very, very special, let's say, asymptotic case of Rényi p-entropy, namely to the von Neumann entropy. Okay, this is of course something what can be considered as our ultimate goal, to say something about the probably most important notion of entropy function, namely von Neumann or Shannon entropy. Okay, but this is something we haven't done yet because this is really a hard problem. Okay, so if it happens that for some given parameter p, we have equality here, okay, for all pairs of quantum channels phi1 and phi2, then we say that the minimal output p entropy is additive. Okay. However, we know that there exist examples of pairs of quantum channels for which we have a strict inequality for some values of p. And this phenomena is known as additivity breaking. So this additivity breaking is something which we decided to address in order to, let's say, maybe rephrase or improve, maybe refine some particular construction, some particular problem which was solved in very interesting paper by Grudka, Horodecki and Pankowski already in 2010. Namely, in their paper, an explicit construction of such states which give additivity breaking for given values of p and some specified dimensions of spaces involved was introduced. Okay, and what we together with Michał did is actually that we a kind of extended or refined those results by providing some, let's say, new constructions of those channels which give additivity breaking by means of refining the methods which were employed in the original paper. Okay. So, in order to tell you about our result, I have to make some introduction to some basic notions of channels. Also, I think that some of you are familiar with this, but I will remind it anyway. So let me start with such fact. We have a theorem which actually can be said that this is a theorem by Steinspring, so-called Steinspring dilation theorem, which roughly says that let us take some linear map which is completely positive and trace preserving, okay, between two C-star algebras, B of H and B of K, and let us focus only on this only on the case of finite dimensional spaces. Okay, so H and K are just isomorphic to some C to the power of some number. Okay, then the theorem says that such phi is completely positive and trace preserving if and only if there exists some auxiliary Hilbert space E and an isometrical embedding V which acts from H to the tensor product of space K, which appears here, and this additional Hilbert space E, such that the action of phi on any element from this algebra B of H can be represented as a composition of partial trace, okay, with respect to E, and with operation which is sometimes called the operator sandwich, okay, with this V. It can be also justified that we can require that such inequality is met between dimensions of the vector spaces involved. I'm not going into this, but it can be shown that we can, let's say, limit ourselves just to the case of such spaces. So what this formula does is actually that it, let's say, pushes the element from B of H, okay, let's say outside of this space, and it actually calculates its image via this operator sandwich in algebra of operators which act on K tensor E, okay, and then something happens, namely this V is applied, and then this additional vector space is of course traced out, okay. So one can think of this like, for example, just like it is done in quantum open systems theory, namely we are, let's say, transferring the initial state, let's say, of such system to the bigger space. We then apply some unitary evolution, and then we are tracing out the environment. Okay, so this is something like tracing out the environment. Okay, and now let us take the map phi from B of H to B of K. Okay, just like this. Okay, so we are taking this formula, and let me name the range of this operator V, which appears here, okay, as a particular subspace W of the tensor product K times E. Now, a technical note, because the theorem says that V is an isometrical embedding, it means that this is a bijection. If this is a bijection, it means that, of course, this is an invertible map. If it's invertible, then, of course, the dimension of its image must be equal to dimension of its domain. Okay, so in particular, this W, okay, this range of V must have the same dimension as the initial Hilbert space. Okay, so this is a constraint. Now, here comes a very important observation. Namely, one can show that many important properties of this map phi, okay, including this minimal output entropy, which we are interested in, depend actually not a particular choice of this isometry, but rather on its range. Okay, so it means that by defining some subspace W in this tensor product K times E, I can define maybe not exactly a map phi, but a whole family, okay, of equivalence classes of maps which share some properties. For example, exact values of those minimal output entropy we are dealing with. Okay, so this approach is sometimes called in the literature as channels as subspaces. And it's, of course, very interesting from purely mathematical point of view. And now what is important is that this original paper by Grudka, Horodecki, and Pankowski involved a particular choice for subspace W. Namely, it was chosen as the CD wedge CD. Namely, it was the antisymmetric subspace in the tensor product of CD with itself. Okay, so that was just the subspace, right, spanned by anti-symmetrized, let's say, vectors spanning CD. Okay, all right. Now, what's the methodology which stands behind detecting additivity breaking? Well, the general idea, which was proposed in the original paper, and then it was adopted also by us, is the following. We choose pairs of maps phi 1 and phi 2, which we hope give us the additivity breaking in a very, very special, very simple way. Namely, we take the second map to be just, let's say, the complex conjugation of the first one. Okay, so this is, of course, a very special, very peculiar choice, right? However, experience shows that this choice is actually enough to demonstrate that this additivity breaking actually occurs. Okay, so the good side of such choice is, of course, such that by defining just one subspace W, I can actually define both channels at the same time. Okay, so both n and n bar. Okay, so the general scheme which we adopted and which was also introduced in the original paper is the following. Namely, we take the space H to be Cm. Okay, so it's m-dimensional. The space K is d-dimensional, and the space E, so this, let's say, environment which we are tracing out at the very end, is also Cd. Okay, of course, because this W must be a subspace in K tensor E, then it's this inequality must be met, right? So the dimensionality, of course, must be less or equal than d squared. Now, how we define these two quantum channels? Of course, the prescription is really easy. Namely, by Stein string dilation, the channel n is simply the just like on the previous slide, okay? And this adjoint channel is just like this, but with V replaced, but its complex conjugation. Okay, so this bar here means just a complex conjugation of all matrix elements of this operator V. Okay, of course, by complex conjugating this V star, a star means a Hermitian conjugation here. Okay, by complex conjugation, we just, of course, end up with simple transposition. Okay, so yeah, of course, this isometry V, of course, has a range W of the same dimension as the initial Hilbert space, just as I told you earlier. Now, because we have to show the additivity breaking, that we have to also deal with a composite or a product channel. Okay, so n tensor n bar will be given by exactly the same type of formulas, namely that will be the trace over E times E, okay, of let's say a dilation of such form. Okay, so this is V tensor V, just like you see here. Okay, and for, let's say, technical reasons, I will be denoting this particular isometry. Okay, V tensor V bar. Okay, it acts from H tensor H into this space. Okay, and it has its own range, W scripted. Okay, which is simply the tensor product of the ranges of both V and V bar. Of course, the range of V bar is the same, okay, as the range of V. All right. So the main theorem, which is actually the source of all possible results, is the following. It's quite technical, but let me at least read it for you. Okay, so let us take two quantum channels, n and bar, just like on previous slide. We make two assumptions. First, we assume that there exists a constant capital C, strictly positive, such that the minimal output entropy of channel n is bounded by the C from below. This is the first assumption. The second one is that there exists a unit vector psi in this space V tensor V, and as a constant small c, also positive, such that when I calculate the p-entropy, Rényi p-entropy of such matrix, such state, it will be bounded by small c, but from the above. Okay, for some p, of course, within this range. Now, if it happens that this small c is strictly less than twice the capital C, then we know that a pair of channels of such particularly simple form n bar generates additivity breaking for given p. And this result was more or less known. It was also more or less present in the original paper, however, maybe not proved in exactly rigorous manner. However, it was there. Yes. a technical note is the following, that it can be shown, of course, I'm not going to do this, but it can be shown that both these bounds, small c and capital C, may be expressed in a very special way by bounding the largest Schmidt coefficient of unit vectors in both those spaces, V tensor V, W tensor W and W, respectively. Okay, so for example, this small c, okay, can be chosen as being equal to such expression. Of course, I'm not going to show you why this is the case, but but of course it can be shown. This is a more or less known result, I believe, from works by maybe Hayden or Hastings. However, what is important is that this bound, okay, for minimal entropy of product channel is actually a function of dimensions of spaces involved. So in particular, this is very easy to calculate. Okay.
Can I have a question now? Concerning this bound. So maybe I shouldn't use my microphone. No?
Now we cannot hear you.
So the question is whether we can find another state for which the bound would be better.
Well, that's a good question. I think this bound is tight. However, I don't remember right now if. Remy, could you turn off the microphone? Thanks. I don't remember right now, but however, I think it is tight. Namely, it can be. No, I don't. I don't know for sure. I don't remember right now. Actually, sorry, but I don't remember.
Okay, thank you.
Okay, just to I don't know, remind you about the Schmidt decomposition in case if somebody doesn't remember, then this is a note. So it can be of course shown that if we have any vector psi in the tensor product of two inner product spaces, okay, including Hilbert spaces, of course, then this psi can be represented, okay, just like by such expression. Okay, so this is just a combination, right, of simple tensors taken with non-negative coefficients, right? Yes, so this is the Schmidt decomposition. Okay, so that was the base theorem. And here comes our, let's say, base result, which is something we proved. So our main result, our main theorem is the following. Again, let us take two quantum channels and bar, okay, just like on previous slides, okay, where we again take this space H to be isomorphic to C to M, K is isomorphic to C to D, with such inequality satisfied, okay? And now, let us assume that if I take any unit vector psi from space W in the tensor product of K and E, of course, so let us assume that the maximal Schmidt coefficient of any such vector is upper bounded by some constant between 0 and 1. Okay, so we assume that those spaces, let's say, of those spaces W have good properties in the sense that, yeah, so in exactly the sense that it is the maximal Schmidt is just bounded. Okay, and if this is the case, then we have the following statements. The first one is that if this fraction, okay, so this ratio of dimensions of spaces W, H, and K is strictly larger than such expression, okay, involving a constant A, which, by the way, is nothing more just than a squared LP norm of such a two-dimensional vector A and 1 minus A. Okay, then we know that such pair generates additivity breaking for given p, which is strictly greater than 1. Yeah, so this is something I should have told you actually at the very beginning. Namely, our theorem concerns only the case where p is greater than 1. Unfortunately, for the opposite, let's say, case of p less than 1, we don't have an idea how to say anything. That's of course some I think good idea for the future. And the second statement is the following: that if this ratio of dimensions is strictly larger than this expression, namely the maximal value, okay, from this set a squared and 1 minus a squared, then we know that there exists some initial p0 greater than 1, such that for all p greater than p0, this pair generates additivity breaking. Also in our paper, we derived some very rough estimation for p0, and this is this estimation. Okay, so this is, let's say, our basic result, our base result. I have written some outline of the proof here. Maybe I will show you. I mean, I would like to show it to you, however, without going into too many details, because that would, of course, consume too much time. So the idea actually to bound those Schmidt coefficients is to use properly and in clever way use the maximally entangled states in those spaces W's. Okay, so here I just denoted those copies of subspaces by indices 1 and 2. Okay, but this is precisely this this space W, tensor W, which was on previous slides. Okay, so so the main idea of the proof is the following: that we take the maximally entangled states between space W and itself, okay, and then it can be shown really easily that the largest Schmidt coefficient, okay, mu1 in cut K1, K2, E1, E2, okay, of this space, of this state, satisfies such inequality. Of course, this is a known result. Okay, and what it gives us the upper bound for the minimal output p-entropy of the tensor product channel. Okay, so this small c comes exactly by let's say from this bound. Okay, so we have the small c. Now we have the following idea, that we can actually let's say use the in clever way the so-called pre-order of majorization. Of course, I assume that you know the pre-order of majorization. Namely, we do something like this. Of course, let us assume, just like the theorem says, that for every psi in subspace W of unit norm, we have that its maximal Schmidt coefficient is upper bounded by some constant A, which is, of course, sharply less than 1. And let us define a k dimension, sorry, not k, but dimension of k was, what was the dimension of k? D, I believe. Yes. So d-dimensional vector A, okay, in the following way. Namely, A has just two non-zero components. The first one is the maximum between A and 1 minus A. The second one is the minimum between A and 1 minus A, and the rest components are 0. Okay? Okay, let me also define a diagonal matrix, diagonal D by D matrix alpha, okay, which is populated by components of this vector. Okay, now let me take any vector W from space capital W of unit norm. Okay, it means that this W, of course, can be put into its Schmidt decomposition in the following way. Of course, K, E, and Fe are, let's say, orthonormal bases which span those spaces K, and E. Okay. Now, let me define the following density operator, rho, which is the partial trace with respect to E of rank 1 projection onto the vector W. Okay, so this is just really standard thing. And after performing this partial trace, I will end up with the expression like this. Okay, so of course that will be the combination of rank 1 projections, okay, onto basis vectors of space K with coefficients given exactly by coefficients of Schmidt decomposition, okay, of this vector W. Okay, so once I have this, let me also define a vector R, okay, which is populated just by those Schmidt coefficients of this state rho. Then what is I'm sorry. Then what happens is that vector rho is majorized by vector A. I don't know if you know the majorization. This is a kind of preorder, and I don't know if you want me to give you some more details about the majorization.
I know it.
Okay. Okay, so assume that
Sorry, a quick question, but you consider here only majorization in the space of vectors, not operators.
Yes, in here,
Okay,
yes,
so
in space
so
of
like
vectors.
standard majorization here.
Standard majorization,
Okay,
yes.
okay. Okay,
Yes,
okay,
yes,
fine,
yes,
thank you.
exactly. Now, what is important is that when R is majorized by A, then we know by a property called the Schur concavity that the that the Rényi p-entropy of rho is greater or equal to entropy of alpha. Okay, so it means that by applying, let's say, the entropy function on both ways, let's say, of this preorder, the order of, let's say, of objects just is switched. Okay, so this is called the Schur concavity. We know that all Rényi entropies are Schur concave, and also the von Neumann entropy, namely this ultimate goal which we would like to address, is also Schur concave. Okay, so that roughly means that this minimal Rényi entropy is bounded from below by such expression. Okay, so that will be true, of course, for all rho. Why we use this approach? Because this entropy of such generated rho, such generated state alpha can be really easily calculated. Okay, all right. So we have something like this, and this is pretty much the outline of the proof. And now two important observations which let's say come exactly from the proof method which we used. And namely, the first one is that it becomes relatively more and more difficult to detect additivity breaking for lower values of P. And unfortunately, for in the case of P being equal to 1, this is well, impossible. So unfortunately, von Neumann entropy, or the Shannon entropy, okay, is immune to this method. Okay, so if you'd like to let's say address the problem of constructing explicitly constructing quantum channels which generate additivity breaking for von Neumann entropy, and we know that such channels exist because it was shown, namely with the proof was non-constructive. However, still we know that they must exist. Then you have to unfortunately use some other method. So yes, this is a drawback. And the second observation is that the subspace which are determined by value of A being close to 1/2 are actually expected to exhibit the largest potential for additivity breaking. And fortunately or unfortunately, this case of A being exactly equal to 1/2 is precisely the antisymmetric subspace which was used by Grudka and company in the original paper. Okay, so this is this case, namely, let me take subspace space K. Okay, so this is this target space. Okay, so that will be just CD. Okay, and let me just take the canonical basis in the space. Okay, and now if we choose W to be exactly the subspace of all antisymmetric tensors in CD tensor CD, namely this W will be the antisymmetric subspace which is spanned by vectors of such form, okay, with this dimension, then a really important observation can be made, namely the largest Schmidt coefficient of such vector of unit norm is bounded by 1/2. Okay, so it means that if we put those two values, namely A being equal to 1/2 and dimension given by this binomial coefficient into our theorem, then this inequality which I showed you, which involves the LP norm, actually gives inequality like this. Okay, so this term must be strictly larger than this term in order for such generated a pair of channels give you additivity breaking. And it is shown to be true for all P greater than 2 and sufficiently large D. Okay, so this is actually the original result in the paper of Grudka and company. Okay, so let's say that the result is a very special case, let's say, of our result calculated for this particular choice of space W. Okay, so that was a more or less everything I wanted to tell you about just the methodology. Of course, the paper itself can be quite let's say problematic, because even today when I was going through this paper once again, try to I don't know, recollect something from my memory from the past, I had trouble understanding parts of it. So so unfortunately it's quite technical. However, we managed to explore two branches of examples of such spaces. Of course, I'm not going to go into too many details, and I will just focus on one branch of examples, which I think is more interesting, namely the first one. The first branch are just spaces W, which are extensions of the antisymmetric subspace, which are constructed from generalized Bell states, which are, of course, known for some time already. And the second branch was subspaces of antisymmetric subspace. Okay, so I thought that maybe this second branch would be not really interesting, because actually nothing bad happens with the upper bound for the maximum Schmidt coefficient. It's still 1/2, but in the first one, things can go wrong. The general idea is that we have to extend the subspace, the antisymmetric subspace, okay, CD wedge CD, by adding some space which is orthogonal to this antisymmetric subspace. Okay, so the W will be just a direct sum of antisymmetric plus something. And now it is the question of of selecting this something, namely, how can we let's say propose a construction of this extension in order to not spoil too much. I will tell you what I mean by this. Okay, so let us assume that this extension X is spanned by some orthonormal basis phi I. Okay, and now in principle, the dimension of this extension, well, could be any between 1 and let's say the the difference, okay, of dimensions of the tensor product, mean d squared, and the dimension of this subspace. Okay, so it can go in principle from 1 to this expression. However, it can be shown that for any, let's say, unit norm vector psi taken from such constructed subspace W, the maximal Schmidt coefficient of this psi is upper bounded by this expression. The PW is just the projection, okay, onto subspace W, which is itself upper bounded by a sum, okay, of a maximal Schmidt coefficient from this subspace, so that will be 1/2, plus some sum, okay, which, as you see, is just a summation of maximal Schmidt coefficients of basis vectors spanning this additional space. Okay, so unfortunately, I told you that fortunately or unfortunately, the greatest potential for additivity breaking is exhibited by spaces with a maximal Schmidt coefficient bounded by 1/2. So in order to generate some examples of such spaces, we would not like to spoil this 1/2 too much. So we would like actually keep this additional term as small as possible. And of course, the natural prescription of this would be to take phi I, which are maximally entangled, because we know that in such case, the maximal Schmidt coefficient, okay, of any maximally entangled state is just 1 over dimension, right? Okay, so we would like this to be actually this space X to be spanned by properly chosen maximally entangled vectors. So the idea for constructing, for choosing such maximally entangled vectors, well, is the following. Namely, let me let me introduce the following notation. Let the space K be spanned by some orthonormal basis Hi. Okay, by tradition, it is enumerated from 0 to d-1, and also the space E is spanned by basis F, also enumerated from 0 to d-1. In such case, it can be shown that the tensor product of K and E can be spanned by a family of mutually orthonormal generalized Bell states, okay, psi Rs, which are given by this expression. Okay, so those omegas which appear here are just roots of unity. Okay, we have something like this. All right, so we have a maximally entangled vectors, and what we would like to do, well, of course, in order to not run into some problems, okay, with the bounds for maximal Schmidt coefficients, of course, we just have to select from the set of all such generalized Bell states just those states which are orthogonal, okay, to this antisymmetric subspace. Okay, so they must lay in the orthogonal complement, and one can actually show that for any d being greater or equal to 2, there exists exactly this number of generalized Bell states which are orthogonal to the antisymmetric subspace. Okay, so we are just, you know, taking spanning this space, this additional space, this space X, by selecting a proper, let's say, subsets of all possible symmetric, let's say, symmetric generalized Bell states. Okay, so the general result, which is also quite technical, however, I will just give you some summary of this, is the following: that if P is greater than 2, okay, so this is the parameter, okay, which defines the exact, let's say, Rényi entropy used. There will always exist some extending subspaces Wn of dimension n. I will specify this in a moment. Okay, such that for dimensions which are greater or equal to 7, okay, we will have pairs of additivity breaking quantum channels. This is the first one. The second one, well, it's kind of opposite. Let's say, okay, for all dimensions greater or equal to 7, there will exist some initial parameters p0 greater than 2, unfortunately, such that for all p greater or equal this p0, we can also generate n-dimensional subspaces, again spanned by generalized best states of orthogonal to antisymmetric subspace, such that they define pairs of additivity breaking quantum channels. And unfortunately, from these two, one can infer the following: that this method is completely useless for detecting additivity breaking when d is less or equal to 6 or when p is less or equal to 2. So unfortunately, those extensions of antisymmetric subspace do not actually, let's say, improve the situation regarding to p, because exactly the same, let's say, constraint on the number of on possible values of p were present in the initial paper. Okay, so again, this is just a sketch of the proof. So the construction goes like this. We know that there exists exactly S of D generalized best states in this orthogonal complement to antisymmetric subspace, and we are taking any subsequence from J1 to Jn of these indices, okay, and we span the n-dimensional space Xn by selecting those best states, but we are just selecting the best states with the indices taken from this vector. Okay. Now, in order to not run into problems, namely, in order not to spoil much, we have to be very careful with selecting the length of this subsequence. Namely, this approach, this method is consistent if and only if, of course, this bound for maximum Schmidt coefficient in such generated space is less than 1. Okay, so when one calculates this expression, okay, so this bound for maximal Schmidt coefficient, this will be this exactly, okay, this expression. So in order to keep this less than 1, of course, this dimension of this space Xn must be less than d over 2. Okay, so when one puts everything, okay, into our theorem, into our inequalities, then we see that the additivity breaking will be observed if such inequality between this term and this term will be satisfied. Okay, and it happens to be true actually for infinite number of cases, roughly when d is greater or equal to 7. Okay, and for from carefully, let's say, carefully chosen p. Okay, so how it looks like. Sorry, just one more. This result actually comes from, let's say, the first part, no, the second part of our theorem. Namely, that was the part which says that if this inequality between ratio of dimensions and the maximal value of subset is satisfied, then we know that there exists some initial p0 such that for all p greater than p0, we will have additivity breaking. Okay. However, the first part of our theorem says that if this ratio is greater than this expression, okay, then we will have additivity breaking for given p. Okay, so this precisely is the following the following inequality, namely this term, which is this ratio of dimensions, must be strictly equal than this expression. Okay, of course, this is quite a non-trivial thing, namely, well, it looks quite complicated. However, one can show that indeed this this inequality is satisfied in actually an unbounded set of pairs PD when P is greater than 2 and D is greater or equal to 7. And I don't know, just to give you some quick summary of the result. So the summary is the following, that when D is less or equal to 6, then of course we are unable to detect additivity breaking with this method. When D is equal to 7, then the minimal P such that for P greater than this minimal P, this inequality is satisfied, is, as you can see, around 3.279. Now, when I increase the dimension D, okay, then of course this limiting number of P goes down, okay, and you can see that for really big dimensions, this P0, this minimal P, actually goes is really really close to 2. However, of course, with this approach, it is impossible to actually reach the number of 2. So this is a kind of limitation, unfortunately, which of course follows from the fact that we generated this branch of examples in a very, very particular way, namely by extending the antisymmetric subspace. Okay. All right, so a quick summary. What we did, the first thing, that we managed to extend the original construction, okay, of those additivity breaking channels proposed in the paper by Grudka and company, okay, onto the case where this defining subspace W is freely chosen, mainly by means of application of more general majorization scheme. Okay, the second one is that with our approach, it is possible to detect additivity breaking for channels defined or generated by the subspace W for P greater than 1, provided that we know the upper bound for maximal Schmidt coefficient of a unit vector in the subspace. So unfortunately, this is a kind of a drawback, because we have to know this limitation for maximal Schmidt coefficient a priori in order to say anything about additivity breaking for given W. Okay, so this is of course can be a technically very challenging thing to do, right? Because in order to find this maximal Schmidt coefficient, you have to actually calculate a kind of you have to maximize, okay, some expression involving the projection onto this projection onto the product vectors and so on and so on. And as we actually experienced, it is a non-trivial thing to do even numerically, unfortunately. Okay, maybe that was a problem of the example which we chose to do this. However, it can be problematic from numerical, let's say, point of view. And of course, yes, we demonstrated that this additivity breaking can be also observed beyond this, let's say, simple antisymmetric subspace. Okay. Now, maybe some future plans. So what we would like to do, we'd like to make the construction, make the method more general. Okay, I don't know how. We had a very stimulating discussion with Rényi, so maybe we have some ideas to do this. It would be very good if we could actually extend this construction onto the case of P less than 1. However, there are more technical problems, let's say, related to such choice of P. Okay, and of course, the ultimate goal would be to, let's say, address or attack the case of von Neumann entropy. Okay, so the limited case of Rényi p-entropy when P goes to 1 in the limit. Okay, so we would like to actually provide hopefully some constructive prescription for examples of additivity breaking channels. Now, yes, I forgot to add a reference here. Sorry for this. However, we know from the literature that the minimal output for Neumann entropy is also not additive. And there is a non-constructive theorem by Hastings, I think, maybe. It was published some time ago. He shows that that it must be true that the von Neumann entropy is not additive. However, he does not give any prescription for examples. Okay, so that would be very good to actually construct something, namely give a constructive proof. And of course, the third thing is to find some new interesting W. Okay, with of course with computable upper bounds for the maximal Schmidt coefficients, which could define additivity breaking, maybe for some just values of p. So yes, so I think this is more or less everything I would I wanted to tell you. So thank you very much for your attention.
Thank you very much, Krzysztof. Now it's time for discussion, questions, or remarks.
So I would be happy to start.
Please.
Yes. So you mentioned this known result of Hastings, which is not constructive, but it requires to show the breaking of additivity going with dimensions, basically to almost to infinity. He showed that for very large dimensions, typically the additivity is broken. And in your case, you have this 0.3, so subspace c to power d times c to power d. So please remind me, so d in your case can be arbitrary, can it be also 2?
Can it be 2? In general, yes, but not in this particular construction, right? Because you have to have the antisymmetric space in this example. But in general, yes, it is.
Yes, of course, the smaller d, maybe you can show this table again. So the smaller d, those tools basically give us weaker results, yes?
Yes,
because
but this is true only for this particular example. Okay, so only by example of extending the antisymmetric subspace by adding something more. Okay, however, you could construct I don't know, something different. Namely, you know, you don't have to base on the antisymmetric subspace. You can just, you know, define the subspace W in any way, right?
Very simple question. Have you found something, let's say for p equal 2, which works for d, let's say smaller than 6, like d equal 2?
We thought we did numerically. But unfortunately, no. The short answer is no. The long answer is not yet, and the longest answer is we had some hope that, for example, I don't know if you know the space by what was the name? Partasarati, yes, Partasarati space of completely completely entanglement, right? The subspace. Yes, by Partasarati. We thought that maybe such space could be a good example. However, we are unable to actually, let's say, create a good numerical results for some reason which I don't understand actually. So this is still a work in progress. So the short answer is no.
Yes, and last question, very simple. Do you believe that in the case d equal 2, you might find violation of additivity for p equal 2, and second one for p going to 1?
I have no idea.
Okay.
No, I have no intuition actually here. Okay. Of course, this is a valid question. Yes, it's worth looking for. Yes, but no, I have no intuition here.
Thank you. Dziękuję bardzo.
Thank you. Any other questions or remarks?
Well, then I can ask. But the problem is that I create the echo because we are sitting in the same place. So in this construction, when you take the antisymmetric subspace and when you add the other one, the x spanned by the Bell states. So this Bell states, the local vectors of the Bell.
Sorry, I cannot focus because I.
Okay, so I will ask these questions later.
Okay.
Okay, anybody else? If not, then Krzysztof, thank you very much for your presentation.
Thank you very much.